Last lecture we derived the incompressible Navier-Stokes equation. I've written it again here. It describes how the flow of a fluid is determined by a gravity force, a pressure force, and a viscous force, by these three terms. Now, away from boundaries, we can often simplify this by finding that the viscosity often goes to zero. And that's what we call an inviscid flow. And it's also incompressible. And in that case, our equation reduces to the following form. And this is what's known as the Euler equation. Euler equation. From the Euler equation, we can derive a different set of equations that is not separate laws, but that can be derived from the Navier-Stokes equation for given conditions. And these are called the Bernoulli equations. And so we derived the Bernoulli equations as follows. First, let's write the material derivative in its split form as we've done in the past. So let's split the material derivative. And let's use index notation. And let's divide the whole thing by rho, both sides. So in that case, we can rewrite our Euler equation as dui. And the body force can be written in a slightly different way, and I'll show you in a second how we get to this. We write it as d by dxi of gz. And this thing here is a body force potential. Why is this equivalent to the form up here? Well, you can think of it as if we take d by dxi of gz, so that is 0 in the x direction, which I'm denoting by the I unit vector here, plus 0 in the j direction, plus minus g in the k direction. And that is simply, this thing here is simply the g vector. And so that's how this term g is equivalent to that g up here. Okay, finally we'll write the pressure gradient term as 1 over rho dp dxi. And so note that we have picked up an extra minus sign here relative to the Euler equation, which had a positive up here. Let's look at the second term in the material derivative here and recall from homework 2, question 3, that we can write this term uj dui dxj as, and here I've substituted Q as the kinetic energy, and that is really just a half uj squared. So in vector form, all of this becomes, so let's take this expression and plug it into our equation 1 up here, and so what we get is the following. So we've substituted the u dot grad u term here for these two terms instead. And the way I've written it, really, this is the ith term of that expression. And then on the right hand side, nothing has changed. Now, for the Bernoulli equation to hold, we make one crucial assumption. We assume that our flow is barotropic. And what does that mean? It means that our density is a function of pressure alone. So we can write rho equals rho of P. In other words, there's, for example, no dependence on temperature in our density. So the ocean, for example, is typically regarded as barotropic, approximately, because the density of ocean water really only varies a little bit with salinity or temperature. It mostly just varies with pressure. The atmosphere is typically not barotropic, since the density of the atmosphere often depends on temperature. So we can write the pressure term as an integral. This term we'll write in integral form as a next step. Write the pressure term. And in order to do that, let's just recall the chain rule for a partial derivative. Recall d by dx j of some function f of p can be written as df dp times dp dxj. And so let's say our function fp in our case here is the integral from some reference pressure P0 to P of 1 over rho, 1 over the density dP dash. And so let's just note here dF dP is 1 over rho P in this case. So if we have that, then we can write d by dx j of the integral P0 to P of dP dash rho P dash as, now using the chain rule, this would just be d by dP of P0 to P dP dash rho P dash times dP dxj. And that is nothing else but simply 1 over rho dP dxj. Since this here is the derivative of the integral of 1 over rho of P.